We are taught a simple truth in school. Diamond and graphite are both made of the same thing. They are pure carbon. Yet, one is the hardest substance we know, a symbol of permanence and value. The other is soft, flaky, and finds its home at the tip of a pencil, designed to be worn away. This presents a deep and unsettling paradox. How can the same fundamental ingredient, carbon atoms, produce two materials with such profoundly different fates? One is a fortress of atomic bonds, the other a fragile lattice. This isn't just a curiosity of chemistry. It points to a more fundamental question about the universe itself. How does nature decide which arrangements get to last and which are destined for easy revision? The standard answer involves thermodynamics. We are told that graphite is the more stable state of carbon under everyday conditions. Diamonds, in this view, are metastable. They are like a ball resting in a small divot on the side of a large hill, while graphite is the ball at the very bottom. This explanation is true, but it feels incomplete. It doesn't fully capture the immense practical difference between them. A diamond does not spontaneously crumble into graphite dust over a human lifetime, or even a geological one. Its structure resists change with incredible stubbornness. We need a more intuitive way to quantify this resistance, a concept that measures the real-world cost of transforming a system from one state to another. This question extends far beyond carbon. Every structure in the universe, from an atomic nucleus to a galaxy, exists in a particular configuration. Some configurations are fleeting, while others endure for eons. What is the universal currency that pays for this permanence? What is the cost to lock in a decision, whether it's atoms arranging into a crystal or a business committing to a strategy? We need a framework that can account for not just the final state's stability, but the energy, effort, and structural integrity required to make a change happen in the first place. It is this cost of commitment that truly separates the diamond from the pencil lead. To tackle this, we can propose a new conceptual lens. Let's think of the universe as a grand ledger, constantly recording the state of things. Every potential arrangement of matter and energy is a draft, but not every draft gets entered into the permanent record. A process of selection and commitment must occur. By understanding the rules of this ledger, what it takes to make an entry final and what it costs to erase it, we can start to build a more complete picture. This framework allows us to translate abstract ideas like thermodynamic stability into a measurable and comparable quantity, a universal price for making something stick. To understand the cost of change, we can use a simple but powerful metaphor: the ledger model. Imagine the universe as a vast accounting system that tracks the state of every particle and field. This system operates through 4 distinct stages: draft, vote, ink, ledger. Each stage represents a crucial step in a system settling into a stable configuration. By defining these terms, we create a clear language to explain why some structures, like diamond, become so incredibly difficult to alter, while others, like graphite, are far more malleable. This isn't a new physical law, but a way of organizing our thinking about physical processes. First, we have the draft. A draft is any possible, temporary arrangement of a system's components. Think of all the ways carbon atoms could connect: messy, ordered, in rings, in chains. These are all potential drafts, the raw possibilities a system can explore. Most drafts are fleeting and energetically unfavorable, existing for only fractions of a second before dissolving back into a sea of potential. They are the initial scribbles in the margins of the universe's notebook, not yet worthy of a formal entry. They represent the full space of what could be before reality imposes its constraints. Next comes the vote. The vote is the natural process by which a system settles on a preferred configuration, based on physical laws and environmental conditions. Thermodynamics and energy minimization play leading roles. Atoms and molecules vote for the arrangement that lowers their overall energy, just as a ball votes to roll downhill. For carbon atoms under immense pressure and heat deep within the Earth, the vote favors the diamond structure. On the surface, under normal atmospheric pressure, the overwhelming vote is for the graphite structure. The outcome of the vote determines which draft is promoted for official record. Finally, we have the ink and the ledger. Ink. The ink is the energetic cost required to lock a chosen configuration into place, making it resistant to future changes. This is the crucial step our metaphor introduces. The ledger is the final committed state of the system after the ink has been applied. A diamond is an entry in the ledger written with very expensive, indelible ink. Graphite is also a ledger entry, but the ink is cheaper, making it easier to smudge or erase. The ledger model focuses our attention not just on which state wins the vote, but on the price paid to make that state permanent and robust against perturbation. The central idea of the ledger model is the concept of ink cost. This is a single, measurable number that quantifies the real-world price of structural commitment. We can define it on an intuitive scale from 0 to 100. 0 represents a system with no structural integrity, like a gas or a liquid. 100 represents a theoretical material with maximum possible resistance to change. Ink cost is not just another term for stability. It is a composite measure that captures how stubbornly a material's atomic architecture resists being dismantled or rearranged. It's the difference between a promise written in sand and one carved in stone. To calculate this value, we must look at the physical properties that directly contribute to a material's toughness and resilience. The ink cost formula synthesizes several key data points. Melting point. Cohesive energy. Cohesive energy is the energy required to separate all the atoms in the crystal to an infinite distance from each other. It tells us how much energy is stored within the structure itself. Shear modulus. Shear modulus measures a material's resistance to being sheared or twisted. While cohesive energy tells us the cost to pull atoms apart, shear modulus tells us the cost to slide atomic layers past one another without breaking the whole thing. This sliding is often the easiest way for a structure to fail, so a high shear modulus indicates structural rigidity. Finally, the formula must also account for the material's phase, solid or liquid, and its specific crystal structure. For example, face-centered cubic, hexagonal, close-packed. By combining these properties, ink cost provides a more holistic and practical measure of durability than any single metric alone. A high ink cost signifies strong bonds plus an interlocking geometry that fiercely resists deformation. Any attempt to change the structure by heat, pressure, or physical force will encounter enormous energetic penalties. It is this high cost that allows a diamond to survive for billions of years, even when thermodynamics suggests it should be turning into graphite. The ink is simply too expensive to erase. To make ink cost a practical tool, we need a formula that translates physical properties into our 0 to 100 scale. While the full mathematical derivation is complex, the core logic is straightforward. The formula is a weighted sum of the normalized values of cohesive energy, shear modulus, melting point, adjusted for the material's phase, structure. The key insight from calibrating this formula against real-world data is the relative importance of each component. It turns out that a material's structural arrangement and the strength of its bonds are far more predictive of its permanence than its melting point alone. Here is a simplified representation of the ink cost calculation. Ink cost, SOCR A, shear modulus, C, melting point, adjustments, phase, structure. In this formula, A and B are weighting factors that are significantly larger than C. This reflects a fundamental physical reality. A material's ability to resist being pulled apart, cohesive energy, and twisted out of shape, shear modulus, are the dominant factors determining its practical toughness. A high melting point is often a consequence of strong bonds, but it does not by itself guarantee structural resilience. Many materials can become soft and easy to deform long before they reach their melting temperature. This weighting explains the diamond-graphite paradox perfectly. Both are carbon, so their fundamental ingredients are identical. Diamond has an ink cost we can calculate to be near 99 on our scale. Its three-dimensional tetrahedral lattice gives it an exceptionally high cohesive energy and the highest shear modulus of any known material. Every atom is locked into a rigid framework with its neighbors. Graphite, in contrast, has a calculated ink cost of around 22. Its atoms are strongly bonded into two-dimensional sheets, but these sheets are very weakly held together. This gives it a low shear modulus, as the layers can easily slide past one another, which is precisely why a pencil works. The preeminence of structure and bond energy over simple composition is a profound lesson. It tells us that in the universe's ledger, how things are put together is often more important than what they are made of. The specific geometry of the atomic lattice acts as a powerful amplifier for the underlying bond strength. Diamond structure creates a system where breaking one bond requires fighting against the entire network. Graphite structure allows for localized, cheap failures. The ink cost formula captures this distinction, revealing that the secret to permanence lies not just in strength but in the intelligent distribution of that strength throughout a resilient architecture. Using the ink cost formula, we can place different elements and materials onto a continuous spectrum of commitment from the most fleeting to the most permanent. This reveals intuitive patterns and highlights the power of the ledger model. At the bottom of the scale, elements have very little structural integrity under normal conditions. Mercury, a liquid at room temperature, has an ink cost of nearly zero. Its atoms are weakly bound and slide past each other with almost no resistance. Helium in solid form, requiring extreme cold and pressure, has an exceptionally low ink cost. As we move up, we encounter familiar metals. Lead has a low ink cost. Tin has a low ink cost. These materials are soft and have low melting points. Aluminum sits in the middle range. Copper sits in the middle range. Middle-range metals can be bent, stretched, and melted down. Moderate ink costs. They are entries in the ledger, written with reasonably durable ink, but revisable. At the high end, we find champions of permanence. Tungsten boasts a very high ink cost, around 96, extremely high melting point, huge cohesive energy and shear modulus. Body-centered cubic structure, densely packed and energetically expensive to deform. This makes tungsten ideal for stability under extreme conditions. The ink used to write tungsten in the universe's ledger is incredibly difficult to erase, second only to diamond. Diamond, the ultimate standard of commitment. The model predicts properties. Tungsten carbide, WC, famous for cutting tools, has an ink cost of approximately 96. This places it firmly in the high commitment category. Conversely, a gallium-indium eutectic alloy, liquid at room temperature, would have a very low ink cost. The ink cost scale becomes a map of the material world. Low, 0 to 30. Mercury, lead, tin. Analogy, writing in sand. Medium, 31 to 70. Aluminum, copper, iron. Analogy, writing in ink on paper. High, 71 to 100. Tungsten, diamond, iridium. Analogy, carving in stone. The ink cost scale becomes a practical index for durability and reversibility across materials. While the ink cost model successfully organizes most materials along a predictable spectrum, its true power is revealed by the outliers. These outliers have ink costs that seem surprisingly high or low given other properties. They aren't failures. They're signposts pointing to deeper physics. They show where our understanding is incomplete and where discoveries might wait. By examining why materials defy simple classifications, we refine theories and uncover subtle complexities of the universe's rules of commitment. 3 outliers are especially instructive: graphite, bismuth, beryllium. Graphite is the best-known outlier. It's made of carbon, the same element as diamond, which has an ink cost around 99. Yet graphite's ink cost is only 22. That gap signals the overwhelming importance of structural geometry. Its extreme anisotropy. Properties differ dramatically along axes. Strong in-plane bonds suggest high ink cost potential, but weak interplane bonds give a catastrophic failure path, collapsing the score. Graphite teaches, a system is only as strong as its weakest link. Bismuth is another fascinating case. For a heavy metal, it has an unusually low ink cost. It is brittle, has a low melting point, and is a poor electrical conductor for a metal. Its crystal structure is peculiar, more like nonmetals such as arsenic than metallic neighbors like lead. That structure arises from complex relativistic effects in heavy electron shells, altering bonding. Bismuth's low ink cost flags that for very heavy elements, simple atomic bonding models fail. We must include relativistic rules to understand its ledger entry. Beryllium presents the opposite puzzle. It's the second lightest metal, yet its ink cost is anomalously high. It is light, stiff. Its properties resemble aluminum and even titanium more than lightweight alkali neighbors. Its robustness comes from an efficient hexagonal close-packed crystal structure and unexpectedly strong, covalent-like character in its metallic bonds. Beryllium's high ink cost shows lightness needn't mean weakness. It's an outlier that pushes materials scientists toward lightweight, high-strength alloys and proves structural commitment isn't only for heavy, dense elements. The true power of a good physical metaphor is its ability to transcend its original domain. The ledger model, with its concepts of draft, vote, ink, ledger provides a versatile framework that can be applied to any system that faces a choice between fleeting possibilities and committed states. Its logic extends naturally from the world of atoms to the realms of information biology and even human society. The ink cost becomes a universal concept for the price of making a decision irreversible. Consider the world of quantum mechanics. A quantum system, before it is measured, exists in a superposition of many possible states, a cloud of drafts. The act of measurement forces the system to vote for a single, definite outcome. This process, quantum decoherence, is the moment the universe's ink is applied. The interaction with the larger environment makes the chosen state robust and irreversible for practical purposes. The information about the alternative outcomes is lost. The ink cost here is the thermodynamic price of creating a classical, stable record from ghostly quantum possibilities. The human brain operates on a similar logic. Neural networks explore countless drafts, different potential actions and simulated consequences. As we weigh evidence and emotion, a vote consolidates neural activity toward one choice. The final decision, the entry into our personal ledger, requires a biological ink cost. This cost can be measured in metabolic energy, the strengthening of synaptic connections, and the cognitive effort of suppressing alternative choices. A simple reversible choice has a low ink cost. A life-altering commitment requires a high ink cost, forging neural pathways that are difficult to undo. This framework is also applicable to organizations and economics. A business exploring new strategies is generating drafts. Leadership and market forces conduct a vote to select a path forward. The ink cost is the investment of capital, resources, and reputation needed to commit. Building a factory, launching a product, acquiring another company. As Dixit and Pindick show, investment decisions depend on potential payoff and irreversibility. A high ink cost makes erasing the ledger entry ruinously expensive. The ledger model provides a common language for the strategic cost of commitment. It is an empirical framework, a lens for organizing our understanding of the physical world and beyond. It offers a quantitative answer to the diamond versus graphite paradox. The cost of locking a structure is measurable from bonds and geometry. A calibrated 0 to 100 scale helps compare materials and predict durability, from super hard coatings to recyclable electronics. The challenge of commitment is universal. It applies to quantum particles collapsing into a single state, to neurons forming lasting memories, and to organizations making irreversible investments. In every case, systems move from possibilities to a single, recorded reality, and that transition has a cost. This ink cost determines permanence. It is the price of certainty. The lesson of the diamond is about the profound value of commitment. Its near-perfect structure, forged under immense pressure, is an entry in the universe's ledger written with the most expensive ink. Some things are built to last because a high price was paid for stability. Understanding the ink cost helps explain the world and build a better one. It guides when to delay and when to commit, writing decisions in indelible ink. Sources: CRC Handbook of Chemistry and Physics Materials, Project Databases.